Well, hello everyone, and thank you so much for joining me today. I'm very excited to present this project. That is the result of a long process that culminated a couple of months ago, but really one of the main uh, components of these projects was to disseminate the idea and to invite people from all over the world to try this website and this technology and the data, because really the idea is to make this openly available so that anybody can use it. So my name is Daniel Acuna. I'm an assistant professor here at the School of Information Studies at Syracuse University. My lab is called the Science of Science Lab and Computational Discovery. And today I'm very happy to be presenting Eileen.io, a recommendation system for grants and publications. So here is with me Rashika Singh. She is a student in my lab, and she will be monitoring the chat, and also I'll be looking at the chat. If you have any questions, feel free to ask at any time. At the end of the talk, I'll have, after the demo, I'll open the floor for questions, and so you can ask through voice or chat there. So before continuing, I would like to thank not just Rachika, but many other students who have helped with this project: Surav, Ananth, Priya, Kartik, Steve, and maybe some of them might be in the chat or in the audience, and some of my PhD students have also helped. And I would like to I would like to thank the funding agencies who helped who believe in this idea to provide funding and create this website, in particular NSF, the National Science Foundation, and also funding from other agencies who have helped in many different aspects of this. Okay, so with that out of the way, I would like to start by sharing with you kind of what is the agenda for today. We have, first, I'll start with the motivation, and this project starts from something very personal because I needed something like this and it wasn't available. So this system helped me, kind of helping myself. So I hope that it helps others. And then I'll kind of discuss how we approach the problem. And from a recommendation system point of view, I'll describe some of the infrastructure, and Rashika actually will describe some of the infrastructure that is behind this website, and some related projects that are using the data or kind of spawned from this project. And at the end, I'll give a demo with multiple, what I think are useful use cases. Okay, so scientists and students that are doing research, funding agencies, many actors in the scientific community are looking for ways of finding relevant research and interesting research. The problem is that, for example, when I started as a junior faculty here in the school, and if you're a PhD student or you're a master's student or just there's someone curious about where to start doing research or where to find interesting ideas, it's really difficult to do it. So when I started here, for example, and I said, well, let's get some funding. Let's see who will be interested in funding my ideas. And the problem was that it was really difficult to navigate all the websites that are available. If you are a student and you'll be looking for example, grants that might be available for you, it's really, really difficult because just the information is too complicated. Now, of course, you can use something like Google, and there are like great search engines, but they're not really specialized for science. And the tools for science don't really work so well. So, but this is a more general problem in science. It doesn't happen just for scientists or students. It also happens actually for the funding agencies. So sometimes, as a funding agency, you're looking for let's say someone submit an application to you, and they say, okay, please give me this amount of money. I promise to do amazing things. But as a funding agency and what is called there a program officer, sometimes you wonder whether the application is relevant and whether someone has already done that idea before, because you want to fund things that are new. So you are also looking for the same issues, basically. If you receive something, you want to find things that are relevant. So as a scientist and as funders, we share the same issue. What are the things that are relevant related to something that we have and that we're looking at now? Now, the way that traditional this is done is by looking at multiple systems. So if you're a program officer or a scientist, you have to look at Google Scholar or Google for finding publications, for finding previous grants in relevant areas. You have to use Federal Reporter, and there are numerous others search engines that can help you with that. But it's all disconnected. There is not really a good way of navigating among them. There's been a lot of advances on this, but still there is a long way to go. So here to the left, for example, I'm showing you, some of you might be familiar, this is Google Scholar. So you search something similar to Google, but it's adapted to scientific publications. And it's probably the most popular way of finding information. But we don't know how it works. So we are scientists and we're using something that we don't really know how it works. So science is supposed to be open, or ideally should be open, especially things that benefit everybody. Okay, so we have the government giving funding, we have scientists kind of sharing information, and if things are open, then everybody benefits, and it's like a free lunch mostly. Now for grants, the issue is a little bit, it's even less developed in the sense that there is not really a good way of searching for grants that have been funded before related to your project. So here to the right, I'm showing you one possible solution that here we use at Syracuse University, and I can confidently say that it doesn't work. I mean, I've tried many times, but it kind of sucks. Okay, so here's I work a long time trying to kind of tweak my profile so that I would recommend funding opportunities that are related to what I do. But as you can see in the examples that I get recommended, they're related, a lot of them to marijuana, basically. So I don't know what they think I would like to apply to those subjects. But thank you very much for suggesting that. So we don't know how they work. We don't know what the data sets they use for making the recommendations. And once we have provided the information to them, we don't know what they do with the data. So if we as scientists and the government, perhaps because they're funding these efforts, many of these efforts, we should get some feedback, like how are scientists looking for information and things like that. But we don't get that information. Now, what has happened over the last couple of years is that there's been an explosion of data sets that has basically opened the door for data science, basically data science applied to science. And if you know anything about data science or machine learning or artificial intelligence, one of the most important components and the success of those areas is to have big data sets. And this has happened in science. So over the last, I will say 10 years, several data sets about publications, about things that are inside publications, such as figures, citations, even data sets that are inside, have become openly available. So this opens the door for a huge array of possible analysis that we can do with data science. And that's basically what we have been trying to do in my lab and many of my students. How we can use those data sets that have become available, bring ideas from machine learning and artificial intelligence to analyze them and help the scientific process. So here I'm showing you a handful of these examples, a handful of this data set. So we have the Microsoft Academic Graph, which is a huge data set of millions of publications, the relationship between them, sometimes the text, sometimes information about the authors. We have Medline, who has publications specifically about biomedical sciences. PubMed Open Access, which makes available images, and we can do analysis of figures. One of my students is doing analysis like that, for example, detecting potential misleading graph in scientific publications. Archive, if you are a fan of deep learning, for example, in data science, well, Archive is the place where all the major, the cutting edge of deep learning is being published at the moment, and that's openly available. Now, on the grant side, also we have a great project now run by the National Science Foundation and the National Institute of Health, releasing basically all the grants that have ever been awarded by around 14 federal agencies, including NSF, NIH, FDA, and other agencies. So we have this big data sets about the publications and about the funding, and it just opens the door for so many analyses. And we, in our lab, are very excited about this. And many other people, of course, are working on these ideas. Okay, so the basic idea of ILEEN and perhaps beyond ILEEN is to take these data sets, and they're great data sets, but one of the issues is that they are disconnected. So we have, let's say, the Microsoft Academic Graph, but that's not really connected to PubMed, for example, which is another data set. And the same thing happened with Google, with grants. So Failure Exporter, which is this data set of grants, doesn't really have a link back to Microsoft Academic Graph. So one of the things that we're trying to do is to take these artifacts that are disconnected and in ILEEN link them together. And we're still working on that. And so this is mostly kind of things that we'll do in the future. But one of the things that we're doing, for example, is to try to organize this information and provide topics for this. So many of the publications don't really have descriptions of what they have, keywords, for example. You just have the full text. And it's really hard to quickly scan information if you have full text, like 300, 400 word description of documents. So it would be good to have something that could be more useful for machines to analyze. So the idea of ILEEN, of this tool, is to basically have something like a helper that will take, let's say, a publication that's a program or a grant submission that a program officer is interested in enriching and trying to find relationship, sending it to the system, and the system will provide the topics, will provide information about the people that are applying to that grant, will provide related publications, related grants, related organizations, related experts. And the same thing will happen with scientists and with students. So if you're a student and you want to find things that are related that you want to cite in your work, then the same thing, you can do it. You can submit it here, and the system will then reach that submission. All right, so now I'm going to review. So there's a question on the chat about the patent. This is not patented, and I probably won't patent it. In fact, we already open the software, and Rashika will explain a little bit of that, but we hope to open everything and make it available. The code is in Python, so it's using like many tools, but the goal is to make it open. So I will review the basic idea behind a recommendation system, and this is more theoretical for those of you who are more in data science and who have perhaps more of a linear algebra background or a probabilistic background. This might be more natural to think about. Okay, so this is the basic idea of a recommendation system. And by the way, this is how most recommendation systems work. If you have used Netflix, YouTube, Amazon, any of those systems that learn from your past behavior, watching behavior, buying behavior, they usually try to recommend things that you are likely to buy in the future. So there is another question. Yes, so I teach, by the way, a course called IST 718 here. and it's big data analytics, and we do exactly this. In fact, one of the sessions is on recommendation systems. So this is the basic idea. So we have, let's say, this is a scientific publication, and we want to find things that are related to this publication. And again, this could be a movie, this could be a book, this could be music, Spotify. So this is just a general document. And the idea is that we want to take this document and extract a fingerprint of the document. We want to basically transform this into a high-dimensional vector that will be a representation of this document. And there are many ways of doing it. For text, we have used NLP before. There are multiple ways of doing it. But the way that we do it for this particular project, if we took these abstracts and we transformed them into what is called a bag of word representation, where basically we just count. This is very simple. We just count how many times different words or bigrams, like combination of words, appear. And then we compute something called a TF-IDF matrix, which basically kind of lowers the importance of words that are very common across the publications. So things like stop words, they will get a really low weight, even though they're very popular. And then we do something called latent semantic analysis, which is basically a matrix factorization of this huge matrix. So at the end, what we end up is something that is very intuitive. So let's say we take a document such as the one that I showed you before, and at the end, what we end up is with a combination of what we call topics. So we transform a document into a mixture of different topics. So for example, a publication on deep learning will have, let's say, a topic on neural networks, a topic on TensorFlow, topic on machine learning. But a publication, let's say, in COVID-19 or coronavirus will have a lot about a topic on molecular analysis, vaccines, like it will be a combination of other things. So basically, we're lowering the dimensionality of this. And the goal is to reduce some of the noise. Okay, so the idea is very simple. So let's say you are buying something in Amazon and you want to get recommendations. So basically Amazon, or Eileen in this case, will take things that you have bought before, things that are found relevant. It will take this fingerprint of topics, and it will do the following weighting. It will produce a weighting that will be things that you have liked before, but it will subtract things that you have not liked before. Things that you say, maybe you gave it a thumbs down, or you said, please do not recommend this movie because I didn't like this movie. And using a very simple equation such as this, the system will make a combination of things that you like and things that you didn't like, and it will kind of push an average of those two things, taking into consideration that there are things that you didn't like. So it will kind of repel the recommendation away from that. Now, how well does this work? Well, we did an analysis of this in the past for another system that is similar, and it seems to work pretty well. So if you compare this to how people use it when they judge similarity between documents, it's very highly correlated. So this is basically saying using human curated distance, like how close humans think two documents or two movies are, whatever we predict with our system, it will be very relative. The other thing that we show is that as the system learns more from you, let's say, and probably you're familiar with this, the more you watch YouTube, the more YouTube learn about your tastes. So the next time you visit YouTube, the better the recommendations are going to be. So this is showing that. So the more you give votes to the system, the lower the distance is going to be, the lower the error. So it's going to learn more and more. Okay, so there is some flattening out. So there is some limits to how much it can learn. Okay, so Eileen. So Eileen, again, going back to the original motivation of this, Eileen is to help junior scientists find publications and grants that are relevant. And what happens is that when I joined here at the school, there was this wonderful administrator called Eileen Allen. So in fact, Eileen comes from her, not, I made up this acronym later. But basically it was a person that helped me find relevant grants. But then this person retired. So I thought it would be nice to name this system after her, because basically, in one way, this system is replacing what she did. So we have an AI system replacing her. Now we have another person, Megan, that is doing a great job, but this could help at least filtering out some of these things. Okay, so now I will hand it to Rashika, and let me find Rashika and ask her to mute. And I assume, Rashika, you can, let's see. You can start your video maybe if you want, Rashika. Great. For some reason, I can't hear you.
Yeah. Can you move to the next slide?
Yes.
So, good morning, everyone. I have been working with Professor Acuna on this project, and I've been a part of his source lab since 2019. I will be going over the explanation of how the infrastructure of Eileen is set up. The major components that I'll be talking about today include Airflow, the Elasticsearch, and the Cayman front end and back end. Next slide, please. Okay. So for Eileen, the major component is a backend pipeline, which includes ingestion of data from multiple sources, storing that data, and topic modeling. Majorly, we use Airflow for monitoring and scheduling the components of the Eileen workflow. Airflow is basically used to track the data ingestion from the sources for automation checks and for refreshing the Elasticsearch indexes. As you can see, the major data sources here come from the publications data, which includes data from Medline, PubMed, arXiv, and the data from grants such as federal reporters. Or the data from all these data sources is ingested periodically and stored into a document, which further is processed for topic modeling. The flow of Eileen includes the various DAGs in Airflow. Some major operations that we perform in the DAGs is downloading the data from the various data sources, persisting them into HDFS, converting the data into Parquet format, and then moving the data for further computations into Cayman indexes. So the end product is the loading of the data sources into our Eileen website. So as you can see the basic structure of our Eileen, the front end is majorly in form of Angular, where a client can interact with the website. The backend is in the form of an application stack in Django, through which a user can log in through Facebook, Google, or connect it to some external site. This interacts with the front end through REST APIs. The ingestion that I talked about previously is shown to the left, where the data from various sources is pre-processed and cleaned by Apache Spark and stored into Elasticsearch as a primary data source. Why are we using Elasticsearch? We use Elasticsearch because it is a highly scalable search engine searching indexes for large scale applications. As the data that we use is really huge, Elasticsearch enables us to perform quick operations. The major data store, we use Kibana to store that index for analysis and for creating the different types of indexes. So Elasticsearch is used as the backend data source, and it has two main components. One, which is the index, and the second, which is the mapping. What is an index? An index is similar to the database, and the mapping is similar to a schema name. We create the mapping, which creates an empty database for us. Then it performs the Elasticsearch data loading. Analyzers are used for looking up the data in the documents. Having multiple analyzers speeds up the operation, which is very useful for a search engine, like in our case. So we use the index analyzers and the search analyzers. The index analyzers indexes a particular field, whereas the search analyzers looks up for an index during the runtime. So here is a snippet of our GitHub repo. This has the code for different data sources that I mentioned, such as arXiv, Federal Reporter, Medline, PubMed, and also has the code for the Cayman loader and the models that we run. As you can see, the various computation takes place from the different data sources, and the final product is that the data gets loaded into our Cayman indexes, which is then used by the front end website. So whenever you perform any search, you can see the data loaded into our search engine.
Okay, so by the way, someone asked before about the course 718, and we go. I mean, this code will like become natural to you because this data set has millions of documents, and if I think it's around like half a terabyte of data, and to process that, of course, you will need either a huge machine or, in our case, a cluster, and to do that to that processing, we use Apache Spark and other technologies that Rashika was mentioning. Okay, so once we have this system built and and you can access through our website, what we want to do is to open this to everybody. We will release the data of how scientists are using this. We want to open it so that other people can use it. So there is a question about whether we found a sponsor. Well, it was funded by NSF, and the maintenance is not that expensive. So we are grateful that the Syracuse has a pretty good cluster similar to AWS, and we can run it there. Of course, if hundreds of thousands of people are using it, it may become slower, but we're constantly looking for funding for this. And so we'll be free to use, and we'll do experiments with this. So we'll do A/B testing, basically things that search engines do regularly. Okay, so how did we validate this? Okay, so we have people who have searched system, and this is a screenshot. I'll show you at the end how it actually looks like. But one of the main things that you have to do as a data scientist is once you build system, you build something for making a prediction, well, you want to see how well you're doing, right? Is your prediction correct? And for search, for recommendation systems and search engine, there are multiple ways of doing it. One of the simplest ways of doing it is to ask the user to give you some sort of feedback. So here, what I'm showing is one aspect of Eileen, where you search something and the systems list documents that it thinks is related to what you search. So here is showing what I searched, Scientometrics recommendation system, and this is the first recommendation that it gives me. And Eileen has an item that, again, I'll show you later, has a button that says, well, I'm interested in this publication, please add it to my library. Okay, so we can take that signal in data science and say, what are the things that the scientists thought was relevant and related this query, kind of just 3 words, with this entire abstract and this title and maybe the authors? There could be multiple reasons why the scientists and the users thought that this was relevant. And Google is the same thing. So when you type something in Google and you put a query and it lists something, what Google is trying to do is to predict that the first result is going to be the most likely clicked by you. So basically, the first result they predict with high probability that's going to be exactly what you will click. Okay, so it's basically sorting by the probability that you will click something, and the more it goes down, the less the probability that you will click it, and then they try to optimize that function. And we're doing something similar. So we did a preliminary study, and we actually improve upon what typical search engines do. So Elasticsearch, you can think of it as a baby Google, like it's a very simple version of Google. Of course, Google is a many billion-dollar company, so we cannot possibly use the same techniques that they use. But we can use something like Elasticsearch, which is an open, or at least is free to use search engine, and for us that will be kind of the random performance, it's kind of the baseline. But we optimize this engine, and based on the human preferences and other information, we are able to improve something called the AUC measure that basically measures how well we're doing compared to something that is a baseline. Okay, so we're able to do much better if we learn from the user. So there is another way of measuring how well we're doing, and it's using the reports from grants. So it turns out that when you get a grant from the National Science Foundation, if you publish something based on that grant, let's say I publish something related to ILEEN, I have to tell the National Science Foundation, hey, thank you for giving me the money for ILEEN. Also, please link this publication to ILEEN because ILEEN funded this. Okay. So another way of validating how well ILEEN is doing is by looking at whether we can predict what are the grants that would have published a certain publication. Okay, so this is kind of reverse. So it's like something that many scientists would like to know. Like if I have a publication today, if I have a document, please tell me which grant would have funded this in the past. And this is a project that's one of my students, visiting students, is doing, Tong, and we had it this year in ASIST as a paper. And this is kind of the general framework. You can look at the paper. I'm going to go back one slide. This is the paper. You can look it up, more details. But basically, this is a framework for evaluating. I think we're using learning to rank, which is a relatively advanced way of learning to rank items. We use a set of features that is standard for search and information retrieval areas. I won't go into the details, but it's just basically a bunch of features, feature engineering basically for this kind of task. And we measure the performance using a way of basically we're trying to predict, similar to what I was saying before, like we want to, the first recommendation of grant, we want it to be exactly what was the one funding the publication. So we want the highest ranking to be exactly what you were interested in. And we get a relatively good performance. These are very high performance because there are a number of assumptions that I didn't tell you, but we're working on expanding these so that there are not so many assumptions. And well, one of the interesting things with data science is that, well, you can get good performance, but one of the things that you sometimes want to do is to understand why you're getting that performance, or to understand why the machine is thinking of the things that you want to get recommended. So one of the things that we analyze is the feature importance. If you're familiar with random forests or gradient boosting, they give you this measure of what the system thinks is important for the prediction. And we found that perhaps obviously after looking at the results, that the things that the system thinks are important are kind of what is the relationship between the abstract and the grant description. So basically you want to publish things that are very related to the grant, and also you want to publish, or you want to find grants that are really close in the temporal dimension to what you publish. So it's not really that surprising. We're basically saying, well, you should get funded on things that are funded similar to what you're doing in the year that you're doing it. So it's not terribly surprising, but I think it's interesting to see the result and to see that the machine is finding the same trend. Now, some of the future features that we want is to get essentially sign up for periodical recommendations. So basically give your email and say, please, every week, send me things that you find are related. So this is an example of an email that we might get from ILEEN saying you should take a look at these publications, at these grants, because they're very close to what you have preferred in the past. Another project that is related to this, sometimes when you're writing a paper or a report for a course, you want to add citations, and it's basically the same problem. Given a sentence, in this case, or a set of sentences or a section, you want to know whether you have to cite something in this context. If you've gone to Wikipedia, sometimes you have articles that have citation needed, saying, well, this claim here should have a citation, so maybe you should put a citation. So, but it's the same kind of technique. We take an NLP technique, we measure something about the sentence or the abstract or the paragraph, and then we'll try to make a prediction about it, or about whether you need a citation. Okay, so this is like details. Again, you can go, I'm gonna go back, you can go to this paper. It was recently published in Scientometrics, and it goes through the details. Now, what we use here is something a little bit more sophisticated. So we're not using, well, we try with topic models, something that I described before that we're using at ILEEN, because topic models are super, super fast. But for this particular project, we use more sophisticated techniques based on deep learning to represent the sentences. And this is, again, this is work by Tong Zhang. We use a attention-based, bidirectional, long, short-term memory network. This is if you're familiar with neural network, this is a neural network, and it's basically encoding the words, encoding the characters. So it's kind of computing a very rich numerical representation of a sentence, and then it's making prediction about them. So there is a question in the chat. So the first question is, does ILEEN have an API and will have in the future? Yes, we'll try to create an API. We have a collaboration with a group in France called Peers we have a small API where we haven't opened it yet because it's taking some time. But basically, the API is recommending reviewers. So if you have a paper, it returns who should review that paper or who should read that paper. Yes, so the second question is, library section in ILEEN has a BibTeX option, and the question is whether we will enable that feature for individual publications. We haven't thought about that. We don't want to get into the area of reference managing yet. We thought, no, we have. I mean, that's a good feature. We haven't thought about it. We thought the library was just the entire thing, but it would be interesting to download individual BibTeX. So for those of you who don't know what that is when you're writing scientific papers, you want to have easy ways of adding citations to other papers. Okay, so for this project that I was describing to predict whether a sentence should have a citation, we did a bunch of tests and we get a pretty good performance. And again, this is perhaps not because we're terribly clever, but just because we have a data set that I think was like 100 or 1,000 times bigger than any other data set from before. So we can use these very rich text representations using deep learning for measuring these things. So we get performance that it's much better than before. So this F1, so it's basically saying we find what is relevant and what we find is relevant. So it's this kind of combination of things that's kind of ideally combining what we desire from recommendations. And here's the demo. I won't go into the demo, but basically you can go here and let's see how I'm doing on time. Yeah, I'm not doing that great. So you can go here and you will get, you can write something. I would recommend, well, here, maybe you should cite something here because it's like a claim that should have some reference to an outside source. All right, so now I'll switch to the demo of ILEEN. And I hope you can see it here. So this is ILEEN. Let's see. All right, so I have my little script of things that I wanted to show you. Okay, so first I need to clear everything because I think I was playing before. Okay, so you go here, ILEEN, and the first thing you find is just a basic search bar. So this is just like Google. And I'm gonna search something, so I tried something before. Well, first when you search, you try to recommend keywords. So let's see, coronavirus. Maybe some of you are familiar with this. So I'm just gonna search this, and it will just search this text in the system. So this is nothing. There is not a lot of machine learning going on. There is not a lot of AI here. No, it won't log in. I think the login is disabled at the moment for performance reason. We'll enable it back later. So this is just searching, saying, does this text appear in any of the publications? Okay, so I'm just searching here. So what I will do, I found this interesting coronavirus infection in cats. This is a paper from 1993. So coronavirus is, of course, a type of virus that is very common. It's not that just the pandemic that we have now. It's been around for forever. So let's say I found this very interesting publication about infections in cats. And what I could do, I could click here and go to the source. So this will like take me to where this is actually being published, so I can see more details about this publication. So let me see. Okay. Okay, so this is interesting. Now, what I can do with this, and here's where the power of recommendation systems come in. Eileen takes this text and makes this kind of fingerprints using NLP, and then it makes a nearest neighbor search to find things that are similar to this text. So when I click here on similar publications, it will do all this process with the backend that Rashika was talking about before. Okay, so I click similar publication, and it will do this nearest neighbor search, taking this. And what's interesting is that because it's taking the topics, it's kind of extracting semantic information. So maybe, so let me see. So for example, here is very clear what I'm trying to say. So here in the main document, you have cats, but in one of the recommendations, you have feline. So in some sense, the system learned that feline and cat are very related. Okay, so that's very important in recommendation systems. It's not exactly the same word, so it's much more advanced because it's extracting a semantic representation of it. And the same thing you can do with grants. So if I click here, it will recommend grants that have been funded before related to this. Okay, so this is not necessarily related to animals, I don't think, but so this is human. So here you have an influenza infection of cats. So you want to go here, maybe go to the funding agency to see when this was funded, how much money they got. So it looks like it had $225,000 for this research. Okay, so I'm going to go back, and I'm going to search again coronavirus because I want to show you. Hopefully I spelled that correctly. So one of the things also you can do is you can filter down results. So maybe you want to search only things in the archive. So there are 3 papers in the archive. Or maybe you want to search things from 2012, things that are relatively more recent. So you can do all of that kind of drilling down of results. Okay, so I'm going to go back again, and I will search deep learning recommendation systems. Okay, so if I've searched that, well, this is interesting. I found something here, so I'm going to click here. And again, so it's like you can narrow down this. You can these are topics that Archive has, so you can drill down on those. And let's say I want to find things. So if you're familiar with deep learning is a concept that appeared perhaps, we were very generous in 2006. I think that was the first time that it appeared somewhere. So I'm going to search for fakes in 2002. So what's going on? How can there be publications about deep learning 2002? Well, they're not really about deep learning. They're not really about neural networks, but you can see that people were talking about deep learning as a way of actually learning something deeply rather than using neural networks. So I'm going to go back again and search this. And let's say I'm interested in this. And here's where most of the power of Eileen comes. So let's say I'm interested in this. So I'm going to add it to the library. And so let's see, I think I went here. Okay, so this is deep learning, and then I'm going to look for similar publications, and you can see that this is all very cool. So let's say I'm looking for this. Okay, so I added those 2 things. So I have added 2 things to my library. So if I go to library, I will have here the document. So I have 2 things in the library. Now, if I go to recommendations, it will take everything that is in my library and combine them. Okay, so what I showed you before is a recommendation only related to one document, but here it will take a set of documents. So here it will recommend based on those two documents that I had before, like what will be the closest things that will combine those topics. So let's say I'm interested in graphs. Okay, so I'm not interested in text, but I'm interested in graphs. So if I add things to the library and then I update recommendations, it will take that I like, and it will recommend things that are related to all the three things that I have in my library. And the same thing will happen with graphs. So here, for example, I have a recommendation system for smoking and for all kinds of stuff. So funding agencies have been interested in recommendation systems before. That's very interesting. Okay, so the last thing that I wanted to show you is once you build a library, so let's say I'm interested in these three things, I can say, well, what's cool is that it generates a unique hash for this library. So I could take this link here, and I'm going to paste it to the chat. And if you click in that link, it will take you to a web page that has these documents. Okay, so I can share this, and I'm going to share this on Twitter. Okay, so it has a button there that will automatically allow you to tweet. So check out what I'd like on Twitter, and I'm going to tweet that, and I can share information. And lastly, you can download these in BibTeX format. So again, this is very specialized for people that work on science, but basically these are so this is not showing for some reason. So let's see. Okay, something's happening. Oh, here. Okay, good. So here, for some reason, this is not showing. But basically, you will see that the results of the recommendations are going to show up in this list. Okay, and with that, I will have my last slide where I thank everybody who has helped me with this, again, my students and NSF funded this. I will open the floor to questions, if you have any. You can, again, visit my website, scienceofscience.org. It has more information about our projects. Of course, you can go to Eileen. And you can go to the information school here in Syracuse. There are multiple professors working on similar topics. So if you have any question, let me know, or maybe Rashika, if you've seen any question.
Hello, Professor.
Hello.
Can you hear me?
Yes.
Yeah, hi. My name is Amber, and I have a little long question for you. So, so basically, I am a grad assistant at the Digital Library program. So my main job is to maintain the Surface repository of Syracuse University, which is the open access repository. So we have around 15,000 records and 26 columns of all the research which has happened in the university over the years. So I was actually, this project was very interesting to me, and I took the 718 class this semester. So I was thinking of how I could do that. I could implement something similar in that. So what were the challenges for you? So for me, the main challenge is that the data which I have is entered by librarians and grad assistants, right? So the data is really, it's not clean at all. So so that is my main challenge. So what were the challenges for you in this project?
Yeah, great question. So as any data scientists know, a lot of the time, or most of the time, is invested in cleaning data. So in this data set, we also have some issues with data. So for example, there is a lot of publications, all publications that are in other languages, such as German, French, Spanish, Portuguese. And so it's hard to know what to do with them because most of the publications are in English, and that's where most of the topics are modeled by the machine. We also have a lot of, so it turns out that when publishers, let's say I publish something, I say, okay, this is my abstract, which is the description of the publication. Then the publisher will add text to it saying copyrighted by, so we have a lot of this noisy data in the abstract, and sometimes it kind of messes up with our recommendation. So I'm glad to hear you're working on Surface. I think that's a system that I looked at before. So, and I think I downloaded it when I came here because I wanted to analyze where my colleagues were working on, and it would be great if you could implement something like this. Again, Rashika knows a lot more about how the back end works, but everything will open it, and it would be great to discuss perhaps in the future about how to implement it with Surface. But yes, like you have to just spend time cleaning data, unfortunately, and at some point it will become easier.
Yeah, thank you so much. So basically, I use the API which is used by the software company called Bpress, which actually has given the software as a service solution to the libraries. So I use their API to generate the data. I have the data right now, but it's not at all clean. So that's my challenge here. So,
okay. Yeah, I mean, happy to discuss further offline. If you're taking the course next semester, that would be a useful project.
No,
too.
I've already taken it this semester.
Oh, you took it. Okay.
Yeah. Thank you so much for the
Yeah,
presentation.
thank you. Thank you for the question. So thank you so much for joining us today. I hope you took something useful from this. At least you can see that in science we're dealing with similar problems that companies are dealing with, but big data and data science is helping us a lot. Again, you can reach out to me or to my students through the usual channels. You can, if you have more questions, you feel free to send me an email or follow me on Twitter or tweet it. Tweet your question, I'll be happy to answer them. And I guess that's it. That's all for today. Thank you so much, and I hope to see you in the future.